Hello, my name is Chris Harding, and I'm an administrator, one of the administrators at Beginning OpenFOAM on Facebook, where beginners help beginners. I'm actually doing Dr. Gohill's extended training, and during that training, he said, if you really want to learn, build the geometry from ground up instead of using my files. So that's what I've been doing, and I needed to build a cylinder and mesh a cylinder so that I can continue on Dr. Gohill's training. And I started out with the simple cavity tutorial so that I can get an idea about faces and hex blocks, the direction, reading the manual, positioning the origin closest to your eyes, and then going in a clockwise direction to specify hex blocks, looking from the inside out, and then looking at the wall and going in a clockwise direction from the inside out and going in a clockwise direction with the points to specify boundary faces. And I think I got a pretty good system down for me. I didn't make hardly any errors except for input errors, but when it came down to the philosophy of specifying boundaries and faces, boundary hex or hex blocks and faces, boundary faces, I successfully did my job correctly. And today's tutorial is probably going to be a somewhat little short tutorial, but the geometry that I'm actually going to be creating today is a half a cylinder, and then I'm going to use this geometry to make the full cylinder in my next session. But as you can see here is my point map, and I all the way up to this point right here is 10R, R being 1 centimeter. So all the way up here is 10 centimeters, and then from here to here is 25R, so that's 25 centimeters. So I use the data from 10R in H over D is equal to 4, and this in this distance from here to here, the inlet and the outlet is equal to H, and I'm and it's equal to 4D, which is equal to 8R, so it's 8 centimeters high. And this flow is going to be flow. You should see some results up by the walls or by the walls and also after the cylinder. But like I said, this right here is going to be the primary purpose of this is to create a half a cylinder for future use, and then to mirror that half a cylinder into a full cylinder, because the cylinder is available as a default tutorial on in OpenFOAM. It's underneath basic potential foam and then cylinder, and it's available in the built-in tutorials, and a person can actually mirror that the way I'm going to be mirroring this. But that's another tutorial after I finish that. But that was my original goal, because Dr. Gohill wanted a cylinder so that we could do flow around the cylinder, do the Stroud number and everything else. And the Stroud number is in between the repeating mins and maxes. And anyways, so the thing is, I use this geometry and this point map in order to create the boundary faces and the hex blocks. And let me open up Genie here. One thing I've done is I've actually, instead of foam clone case and cloning a new case from a past tutorial like the small rectangle that we did last time, I actually copied the tutorial from the built-in tutorials, and then I changed the points according to what I told you over here, which from this point to this point, point 2, is 10R, and this is R is 1 centimeter, and then from this point, point 3, to the final point, which is point 5, is equal to 25R, and that is equal to, all these points are derived from that and from the trigonometry associated with this angle being 45 degrees and splitting these in half. And then for the arcs, it's going to take this 22.5 and then getting the interpolation points for each one for the arcs. And we have to, and that will come later. But according to this geometry, and what I specified with 10R, 25R is how I got these points. I specified a total of 19 points because this is copied. 19 points were specified for the first, and I decided to go with 19 points this time, primarily because there would be too many if statements to specify to grow a point, and it doesn't make sense when it's just easier to specify it in this case. So I specified all the points, and then I used the same Z configuration for the cylinder, which from the pointField.H for the tutorial is in the cylinder, by the way, for the built-in cylinder. And then I put in the info points for the points, so print out the points. And then for this hex block right here, this is number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10. 10 hex blocks. And for this hex blocks, the first hex blocks, we would have to turn this according to the manual because 0 is left, 19 is right, and the left means that it's in the back and back plane, and the 19 right means that it's in the front plane. So the back plane being the smaller numbers in this case, in this block, it's going to be 0, 1, 7, 6, because if we turn this and go clockwise, it's the same as going counterclockwise without turning it. So 0, 1, 7, 6, 19, 20, 26, 25. And we got 0, 1, 7, 6, 19, 20, 26, 25 right here in this first row. And that's the first block. And we just did a meshing of 10, 10, and 1 for all these, just to show that when we're finished meshing that lines are supposed to match up. I'm not expert on meshing, but I'm learning a little more that I'll mention in this tutorial as well. And about when we go from a fine mesh to a large mesh, the maximum size is 20% larger than the fine mesh for the coarse mesh. And so anyway, so that's how you specify blocks. You, if you turn this page, on this page there's other drawings on the other side, but if you turn it, then you'll get, then the 0 will be on the right hand side and the 1 will be on the left hand side, and then we would go counterclockwise and it'd be 0, 1. The 7 would be on the left hand side and the 6 would be on the right hand side, so it'd be 0, 1, 7, 6. But if we go, since we don't turn it, we can go in a counterclockwise direction, 0, 1, 7, 6, and we get the same result. So I did that for each one of these blocks. This block right here is 1, 2, 16, 7, and you can see over here that is 1, 2, 16, 7, and then 20, 21, 35, 26. 20, 21, 35, 26. Counterclockwise for both. I did that for all the hex blocks, and these are the values for the hex blocks. There's a total of 10 of them as I specified. Now the arc. This can be a little confusing. It was for me anyways, reading in the manual. It talks about interpolation point. It seems like there's only one point you need to worry about, a point in the center, but it's not quite, in my opinion, well explained. And in order to, we need to get a point on this arc between these 2 points right here, an interpolation point that we can use to specify the arc. So we see here, this is going from point 1 to point 7. And point 1 is this arc right here from point 1 to point 7. And for the, I did this arc, this arc, this arc, this arc, and then this arc, this arc, this arc, and this arc. And then I copied those down here because they're the same numbers. And I copied those down here because they're the same numbers, and I had one off there. And what I need is I need an interpolation point and I say halfway, so halfway between here and here is half of this angle, so that's 22.5, and I'll bisect it in half. The angle 22.5, and this length right here is 2 centimeters, because this length right here is 1 centimeter and this is another 1 centimeter out, so it's 2 centimeters. And so it's going to be 2 centimeters cosine 22.5 will give the distance here to right here, and then we take 11 minus that in order to get the x distance, and that comes out to be 9.1522489. When you do the arcs, you want to go out with as many decimal places as you can, because it has to be between 2 points. You're going to be trying to create a circular cylinder, so you want it as accurate as possible. So the arc, once again, is from point 1 to point 7, point 1 to point 7, and then in order to get the x value, which if you drop this down and you'll have a triangle, in order to get this x value right here, from here to here, you take 11 minus whatever x is. X is equal to 2 cosine theta, because this distance is 2, and cosine theta is equal to adjacent over hypotenuse. Hypotenuse is 2. The adjacent is the distance we're trying to get. So 11 minus that distance gives us 9.1522489, because 11 is this distance right here. This is 10. This is 11. This is 12. This is 13. So that's how I did the arcs for all of them. And I'm not going to go through all these arcs. But for the faces, you want to look on the inside out. So I'm going to do the inlet face. And if you see the inlet face here, we're looking from the inside out. So we got 6 on the left. Remember, 25 on the right. That means 6 is in the back. 25 is the front plane. And 11 is the back plane, 30 is the front plane. So if we're going to go clockwise, if we're looking from the inside out, if we're going to go clockwise on the face, that would be here, that if it was three-dimensional, and the 25 would be forward. But if we're going to go clockwise on that, we have to go 6 to 25 to 30 to 11. And that's 6, 25, 30, 11. And then down at the bottom, we would go 0 to 19 to 25, 6. 0, 19, 25, 6. I try to start out with small numbers, keep it that way so it's easy to read and follow. And I followed the conventional numbering of going from left to right, from 0 from left to right, and then all the way up, and then numbered the last two numbers, 16, or last three numbers, 16, 17, 18, after figuring out the number for this, which is 15, down here for this, for what will be part of the circular cylinder. So I wanted to mention that real quick. So that's how you specify faces. Once again, so if we did the outlet over here, and if we did the outlet, then we would have, looking from the inside out, this time 10 is back, 15 is back. We got to go from 10 to 15, 34, 29, because we're going in clockwise direction. So that's like this. So we have to go up from 10 to 15. That's the back plane. Front to the 34 point, and then down to 29 point. So it's 10, and that's the back wall, or that's the outlet rather, excuse me. And it's 10, 15, 34, 29. And then it's 5, 10, 29, 24, 5, 10, 29, 24. And simply you have to do all that for the rest of these. Now for the actual cylinder, we want the wall to be on this face, this face, this face, and this face. We don't specify anything on this face, but we specify this to be a wall. It's going to be no slip, and it's going to be a no slip wall. And so we specify we have to look from the inside out, and then clockwise would be 2, 16, 35, 21. And this is 2, 16, 35, 21 right over here. So it shows you that, and this is specified as type wall. Inlet and outlet were specified as type patch, and this is specified type wall. And the symmetry plane just allows, as I said before, allows for a better calculation of the data. From what I saw in a quick explanation of it, it provides more accurate results. It doesn't squish the results so severely or affect the results so severely. And I'm learning as I go with this. So remember, I'm a beginner, and this is beginners helping beginners. But that's how I specified all the patches right here for the actual cylinder wall. And then front and back, you don't have to specify these. You can leave these out if you know that you did it right. You can leave these out, and then it'll automatically create default faces, and then you can name those empty. But I like, since I'm doing this for practice, I went ahead and specified them. And the only problems I had when I ran this the first time was I had a lot of input errors, transcription errors. And so this time, and it was easy to follow. It basically told me it was out of range. And for example, instead of 29, I had 39. That was out of range. And so, but now we have this, and we have, let me change this to point field. Change the, now let me see. I've already done, let me do foam clean tutorials because it's just a good habit to get into, even though I've already cleaned it. In foam clean poly mesh, and then block mesh. In order to run this block mesh so that it works fine, if you don't specify the 0 and the P folder, so if we go here, in the 0 folder, if you don't specify the P as P original and the U as U original, and then it'll give you an error, and it'll tell you that that some information is missing. And so if you change these to P original, U original, then it'll mesh it and create the blocks without causing a problem. So let me go ahead and take a look at the mesh first. Okay, so that's canceling. So let's try para view. I'll get it one of these times. And I haven't figured out why it's closing, but it'll open in ParaView and will open in ParaFoam. I haven't figured that out. Okay, so it's solid color, and let me go ahead and go to the surface with edges. You can see here, I'm not an expert on meshing, but to tell you, when you go from a fine mesh like this to a coarse mesh, this block, this cell, should not be 20% larger, should not be greater than 20% larger than the smaller one. So, and then you can do a gradient from that point forward. So this block, this cell right here, and these cells right here should not be 20%, should not be greater than 20% larger than this cell right here. And then once you have that cell, you can do a gradient to your final cell, whatever size you want it to be. And I've shared the gradient calculator in the past, and I'll share it again underneath the info or in the info for this video tutorial. But this is the mesh, and as you can see, mesh fine. It created the cylinder fine. Oh, I see one area problem, and I just realized that, and I'm gonna have to figure this out. So it didn't, for some odd reason, from 1 to 7, it didn't actually do all the cylinders. So let me see if I have 1 to 7 arcs specified correctly. So let me pause this. I discovered that the error was one of my points in my block mesh dictionary was out of range. I forgot I had 99 right here. I deleted that, but then I forgot to save this and run block mesh again. So I had 99 here. I deleted it, so it was giving me an error, but now it's fixed. So anyways, that's the block mesh file. And let's go ahead and look at the block file. Here's the block file with the points. And once again, this is a customized domain, and this has a height to diameter relationship for the outlet and the inlet, the of equal to 4, and it should be a good domain, geometry domain for doing some comparisons. Um, so anyways, this is it for this tutorial. I hope you enjoyed it. Let me go ahead and go to, instead of going to the code, it's pretty simple. You can just look at the cylinder and the tutorial, the built-in tutorial, and look at the code there, and it's different coordinate numbers, but different point numbers, but it's the same code. Um, so anyways, I hope you have a nice day, and I hope you found this useful. Thank you, and have a good day.